So in today's class, we're first going to talk about frameworks, and I'll talk about how frameworks apply to various parts of Android, and we'll talk about how frameworks can get built up into software product lines, and then I'll talk about the particulars of some parts of Android having to do with user-facing operations and classes and components, and then we'll talk about the first programming assignment. So we're going to start off by talking about something called scope, commonality, and variability analysis, which is a method for developing frameworks and other kinds of systematically reusable artifacts. So you'll get a chance to learn about SCV. And then after we talk a bit about SCV as a method, then we'll talk about how you might apply SCV to understand some of the elements that go into the Android architecture. So it's just good to have this overall perspective. So before we get into scope, commonality, and variability analysis, let's talk a little bit about something called a software product line. So the previous discussions we've had here last class were about frameworks. And if you recall, a framework was an integrated set of classes that provide a reusable architecture for a family of related applications. So the idea there was systematic reuse, parts that work together, parts that provide inversion of control, domain-specific structures and behaviors, and semi-complete applications. And that's very useful. But what's even more useful, although not as often practiced as we might want, is to combine the concepts of frameworks together with other forms of systematic reuse, things like patterns, things like class libraries, things like components and so on, or middleware, and to combine those things together with other tools like model integrated computing or model driven engineering, and put it all together into something called a software product line. And this is kind of the holy grail of systematic reuse. Not always realized, but a very important concept to understand nonetheless. And you'll see also how it really figures into what Android is, because Android, among other things, provides a software product line for developing mobile applications. So a software product line is a set or a family of software-intensive systems. And when we talk about a software product line, we're always talking about this notion of commonality and variability. Some of the things that are part of the software product line are common to all the different applications that use the product line. Other things in the product line are hooks that are intended to be customized in order to handle different variations for different types of products that use the product line. And the various products and services and applications and infrastructure and so on are all developed by reusing the assets of the software product line. Now, in the context of Android, this is really straightforward. Android and to some perhaps lesser extent the iOS infrastructure are fantastic examples of software product lines because they do exactly what you want to have done with software product lines. They have great support for systematic reuse. So, for example, if you think back to the way people used to build smartphone apps or feature phone apps as they used to be called, people would develop the hardware, and then they would develop the software and the operating system and the drivers and the various layers of middleware in a very ad hoc and customized way, which meant there was very little leverage or systematic reuse. It was only opportunistic reuse. Opportunistic reuse is the reuse you get when you cut and paste code from one program to another. Does anybody know why cutting and pasting with opportunistic reuse is a problem, even though it might make you more productive in the moment? Yeah?
Then when you need to change something, you have to change it in multiple places.
Exactly. So the minute you start cutting and pasting, then you make a change, you find a bug, or you have a new feature, or you want to port to a new operating system, or you've got a better algorithm. You have to go back not just to one, not just to two, but to all the various end places where you cut and pasted that code. And that quickly gets out of control. If you ever wonder why so much software we use day in and day out is known as bloatware, it's because people have applied cut and paste approaches to reuse, and you'll find string classes or file classes or all kinds of other stuff just cut and paste and modified many, many different times throughout the source code. So the nice thing about systematic reuse is we don't have to apply those changes so many times. You put it in one place or a very small number of places, and then you customize through the techniques we're going to talk about here. So think about what Android does. You get a pile of code if you are a vendor like HTC, or you're a vendor like Samsung or Motorola or whomever, Huawei, whoever's the provider of, or Amazon, I guess these days too. You take the Android source code, and a lot of that source code is very common. The source code is sort of independent of the particular hardware. It's independent of the particular details of the devices that are connected. It might even be independent of the user interface in some cases, depending on what kind of skin that is provided by the manufacturer. So there's an awful lot of stuff that's common, but then people come along and they customize it in various ways. They add a different look and feel. They add different kinds of hardware. They add different kinds of drivers. So those things vary. And of course, then people who develop applications also have lots of variability as well, but they use a tremendous amount of common core capability. So that's really crucial from the context of a software product line. Not surprisingly, there's a big relationship between frameworks and software product lines. Software product lines build on a lot of other technologies besides frameworks, but frameworks and the thinking that goes into building frameworks are core for a software product line because they help you to think about decoupling the general purpose stuff from the more domain-specific stuff. They think about how to handle these variabilities in a consistent way. There's a lot of other information you can read about on software product lines at the Software Engineering Institute. There's a whole website that has material there, and they've written books and had case studies and tutorials and other things for quite a long time in this particular topic. So using a software product line or a framework is tricky enough. You have to learn a lot of stuff, and you guys will learn a lot of stuff in this class in that context. But it's even harder to develop a software product line or a framework. And that's because you have to be able to anticipate all the different uses people will take this common, systematically reusable pile of code and apply it in all kinds of different new ways. Some ways that may not have been anticipated by the initial developers of the software. So that begs the question, how do you do that? How do you go about building a framework? How do you go about building a software product line? And that's what we're going to talk about here. Not so much because you're going to spend a lot of time, at least in the beginning of this class, developing frameworks or software product lines. We'll do some of that towards the end of the semester. But it's really important to have a good appreciation for the effort that goes into doing this kind of stuff. And you'll occasionally run across people who do not think it is possible to achieve systematic reuse. I was having a discussion with someone the other day who was arguing with me vehemently that reuse was a waste of time, couldn't imagine why anybody would do this. I wasn't honestly quite sure what they were proposing instead, but you start looking around at the things that you use to build software with. Things like libc, things like Unix or Windows or Linux, things like Java virtual machines, things like C++ compilers or interpreters for various languages. You think about the middleware that we use, like Android. And you sort of scratch your head and go, what are you talking about? Reuse isn't important. You couldn't imagine to begin to build software today if you weren't applying systematic reuse somewhere along the way. The trick is that most people don't end up being producers of reusable artifacts. They simply end up being consumers. So a big part of this course will be to help you become educated consumers of reusable technology. But it also helps to know how to build it, because invariably as you get further in this course, and certainly as you get further along in the work that you may do, you'll end up having opportunities to build reusable assets. Now, anybody here who's developed software commercially, either as a consultant or in some other capacity, has anybody here ever spent time building reusable artifacts? Christoph, what did you end up using or developing?
A bunch of widgets for Android.
So usually what happens here is you don't start from scratch. You don't build an operating system and a user interface and all the middleware by yourself. You start with taking something, much like that funnel example I showed you in the last class, and then you add stuff to it. So the question is, why would you do that? Why would you want to develop that kind of stuff? Well, my guess is, without putting words in Christoph's mouth, you can start to find ways to leverage that for other projects. So whether you're a consultant or you work for a company or you want to start a company, you want to be able to build up assets that will make you more competitive, make you have an advantage versus other people. That's why I got in this in the first place when I started back 25, 30 years ago. I wanted to be able to work on a lot of different projects, but I didn't want to have to go and reinvent all these things repeatedly over and over again at great expense. So I started building my own frameworks, my own infrastructure. And that blossomed in a variety of different directions. But the point is, it's a great way to be competitive, and it's a great way to be able to get things done faster once you've taken the effort to build this infrastructure in the first place. So crucial to this is the concept of scope, commonality, and variability analysis. And I'm sure you've all remember the things, maybe you don't remember this stuff, but when you're a little kid, one of the things that you do a lot is you look at pictures and you're supposed to identify which one of these doesn't look like the other. So my 6-year-old son, when he was much younger, we'd look at pictures of pumpkins, and you had to find the one that didn't have the hat on it or something like that. So that is very early training to become good at scope, commonality, and variability analysis, believe it or not. So you're always looking for the thing that's common and the things that differ, hence the picture here. You can apply this particular process, and I'll go into a bit more detail in a second on the method involved, to identify commonalities and variabilities within a particular domain. Now, the domain issue is important. That has to do with the thing we're going to talk about later called scope. Let's just assume, for sake of argument, we're going to use the Android libraries or the Android frameworks as the scope for the moment to make the next discussion relevant. By the way, there's a good article you might want to take a look at that you can get at this URL, which is in the slides. And it's by some of the early people who did a lot of work on commonality and variability analysis, some folks at Bell Labs who were working on systematic reuse, infrastructure, and product lines, and frameworks, and so on, and technologies to support these kinds of things. And they have a nice article that talks a bit more formally and thoroughly about commonality and variability analysis. So, as I said before, we use this to guide the development of product lines and frameworks. So here's the general method in a nutshell. Now, the great thing about this method is you can apply it recursively at many different levels of abstraction in many different application or system infrastructure domains. We're going to focus on Android here just because that's the topic of the course, but be aware you could apply this to just about anything. In fact, to some extent, what I'm about to tell you is the essence of good object-oriented design, or just good design in general. So what you do, wherever you are, whatever level of abstraction you're going to start with, one of the first goals is to identify the common properties or common portions of a domain, things that are consistent, and then define a stable interface to those things. Now, to some extent that begs the question, how do you know something is stable? And the best advice I can give you there is it comes with experience. As you start to develop software for over a long period of time, you begin to realize some things change a lot, some things don't change very much. Or if they do change, they change at well-defined intervals. For example, if you developed accounting software, if you worked for Quicken or someone, things change, and they typically change around tax time, right? So when it's tax season, people have come out with a whole new set of tax codes, and so you can be prepared for changes that take place in that time frame. So in this context, let's just use a very simple example where we're dealing with the Android async task mechanism. We kind of talked about that before, and so let's just talk about it just for a second. So the async task defines a stable interface. The interface gives you a couple of methods. It gives you the execute method, which is called to start the task up to do its thing, and then it defines a couple of the other helper methods called hook methods or primitive methods. And that's the stable part. Now, you can imagine that this didn't just fall out of thin air. People who were doing Android probably sat down for a while and thought about, what are the various forces we're dealing with? What are the constraints? One of the constraints they had was they didn't want to block the main thread of control for any length of time. They wanted that to be able to be responsive to input events from lots of different sources of input. So they said, let's go ahead and run some things in the background, but they didn't want to have the background thread be responsible for coordinating and synchronizing with widgets that are used to display information in the user interface. So they said, well, we can't have the background thread just willy-nilly talking to the user interface thread. We have to figure out some way for them to coordinate with each other. So they came up with a bunch of different ways to do that. And they defined a common interface for that. And the interface includes various hooks like on pre-execute and post pre-execute and on progress update, and so on and so forth. By the way, another question for the Android gurus in the class. Why is it that background threads are not allowed to access user interface widget resources? What's the reason why they can't do that? This is actually a very, very common pattern in most user interface code. You can only have one thread of control that's actually accessing the display. Christoph.
Well, first of all, the event dispatch loop owns the UI thread. Secondly, it's to be responsive. You don't want to have to deal with all the inherent complexity of synchronizing on all the views. So it's just faster code if you run it only on one thread.
Interesting, yeah. So there's a couple different things there. So back in the early days of user interfaces, everything started out single-threaded, if you go back 20, 25 years. And so user interface code didn't have to worry about things running from a background thread because it wasn't running in a background thread. It was running in the foreground thread. There was only one thread. So people wrote an awful lot of code at the time that didn't know anything whatsoever about reentrancy or thread safety or other kinds of properties that involve synchronization. So there was this pile of legacy code that just sat out there. And as people started to add multi-threading to operating systems, to things like Solaris back in the early 90s, to Windows kind of in the mid-90s, to Linux a little bit later perhaps, but around those times, then you had the option of being able to do some code that was in other threads and some code that was in the user interface thread. But because people had written all these user interface libraries that were not thread safe, they were not reentrant, meaning that if you made a function call and then that function got called back again from another thread or from a recursive call, it would disrupt internal state. People said this is way too much trouble to try to go back and retrofit thread safety into that user interface code. Let's just come up with patterns and architectural themes for decoupling the threads that run in the background from the thread that does the user interface interaction. When people moved to later systems like Java and Android and things that were based on Java, at that point, threading and synchronization was firmly part of the language abstraction. People were using that quite often. But it still became the case that people were putting one thread of control to run the user interface interactions. And the main reason there is that it is going to be simpler to write that code if you don't have to be concerned by having people changing the user interface out from underneath you at any given point in time. So requiring people to have to learn about synchronization if they're just writing fairly simple code seemed excessive. So they kept a lot of that logic out of the user interface parts of the abstractions. So we end up with what we have today, where you don't have to worry about multi-threading in the user interface code, but you have to make sure that your multi-threaded code doesn't try to write to the user interface. So popping back a level and talking about the commonality part. So there's a commonality part in this context. It's the interface of async task. The next, and that's usually fairly simple. If you play around with a domain long enough and you've got domain expertise, knowing what's common is typically not too mysterious. Much more difficult thing to do is to figure out what's going to vary and then to define a stable interface for variability. That's a much, much harder thing to do, because the minute you start dealing with variability, the minute you start having different ways of doing things, it's often easy, it's tempting to just start having gratuitous ad hoc variation. You could have different interfaces to do things in different ways. And so if you're not careful, if you don't think about your software design in a very systematic way, you start having variability take on different ad hoc custom personas and interfaces. So the really hard part is to figure out what varies and then make that variation have a common interface. So a couple of specific examples of this in the context of Android and async task. They defined a bunch of things that could vary. Things that can vary in the context of async task include the parameter that you're used to run in the background, the thing that you're going to pass to the background thread in the doIn background hook method that runs in a separate thread. Likewise, there's a data structure that indicates progress. As you're making progress processing, you can communicate back to the user interface thread the progress, the status, through the onProgressUpdate hook method call. And then there's also the result, the thing that is done when the computation is finished running. So those are all things that vary, but we come up with a way to make them vary in consistent ways by having them template parameters to the async task generic type. So they're parameterized types. I guess they're not templates because it's Java. They're generic types that are passed to the generic async task. So that's one way we have variability, i.e. things that can change, have a common interface. Likewise, we also have the signatures for the hook methods. So things like on pre-execute, on post-execute, doIn background. Those methods are also defined with very specific interfaces, and you as an application developer who want to customize async task can simply come along and subclass and override those methods in whatever way you feel is appropriate to get the job done for you. So the goal there again is to have commonality in the way that we have variability. And then the last piece of the puzzle is to be able to bundle up different implementation artifacts and have them be applied as plugins. Now the async task model that we're showing here doesn't really illustrate this in its full-blown glory. If you go back and watch last week's video and look at the discussion of the executor portion of the async task framework, the so-called black box portion, that's a little bit better example of how to do a plug-in, where you're actually creating an object, an executor object, for single-threaded or multi-thread pool or customized executors, and you're passing those things into the async task object when you create it, or when you set a certain method. That's a good example of black box plugins. That's even a harder thing to do because you really have to anticipate the way in which stuff gets developed. But that's the basic model of developing frameworks and product lines. Find what's stable, define an interface for that. That's usually pretty straightforward. Find what varies, define a stable interface for that. That's a lot harder. And then be able to plug in somehow or another through inheritance or some kind of callback object or strategies or policies or whatever you want to call these things, depending on what paradigm you're working in. You plug those things into your framework, your product line, in order to be able to get controlled variability. And when we go through the various examples here in Android, I'll show you lots and lots and lots of examples of how commonality and variability apply in Android. And it's there because it'll help you understand it better when you use Android, but much more importantly, if you really get this paradigm in your brain, as you build your own frameworks, as you build your own software, you can apply this as well. There's some other stuff out there that's worth taking a look at, something called Solid. See if I can bring up a browser that'll show that easily. Otherwise, I'll just switch over and do it. So if you take a look here, there's a design methodology called SOLID, which stands for Single Responsibility, that's the S, the Open-Close Principle, that's the O, Liskov Substitution, that's the L, Interface Segregation, and Dependency Inversion. And I'm not going to spend a lot of time on this right now. We're going to cover this later in the course, but it's a really good set of things to understand. A lot of this stuff was identified by my good friend and colleague Robert Martin, who's been doing design and patterns and frameworks and product lines and agile and all kinds of other cool things, test-driven development for decades. And these are some really good things to understand because as you build your software, you'll find yourself using it over and over again. So we'll come back and talk a bit about that as we get a little further on in the course. Okay, so given that as a background of a paradigm and a little bit of example of showing it on a postage stamp sized piece of Android, let's talk a little bit more about how we might apply scope commonality of variability analysis to think about Android itself at a more macro level. So at the top level, let's talk about Android from the point of view of scope. What's the scope of Android? And it's actually pretty interesting. If you go and you listen to some of the talks given by the developers of Android, a good place to look would be some of the Google I/O conference talks that they typically videotape, and you can see the slides and you can see the presenters talk about the stuff. There's some really good talks that illustrate the scope of Android, what it was they were trying to solve. And one of the things that really comes across, especially in the early talks back in the 2007-2008 timeframe, is the fact that they were trying to build a solution for resource-constrained devices. And it's interesting. If you go back and you watch, I think Dan Bornstein's discussion about Dalvik and some of the other discussions about how they came up with some of the architecture decisions that are part of the anatomy and physiology of Android. You'll see a lot of really interesting discussions about how they came up with ways of trying to use native methods a lot of places to avoid having to have too much Java code running, so you could have more native code executing to make execution faster. You'll see the discussion about the Dalvik virtual machine, where they used a register model as opposed to a stack-based model of interpretation and processing of the bytecode in order to be able to save power. There's a lot of discussion actually in Bornstein's discussion about the way you should do loops. There's certain ways you should loop in Android using Java in order to maximize or minimize power consumption, which is kind of an interesting thing. People don't think about that a whole lot, but the for each loop, I believe, is one of the things that they recommend, because there are ways that they can optimize that in terms of power consumption. Lots and lots of other cool stuff there. Another good thing that they have in Android is this concept of something called the zygote. And when Android boots up, they have a pre-configured process called the Zygote process that's got pretty much all the libraries, all the Java libraries, all the standard Java libraries, all the standard Android libraries, all loaded into the address space of the process. So you can imagine it's a pretty big process. And whenever you go ahead and launch a new activity or you launch a new service, all that happens is it goes ahead and it dynamically loads in your activity or your service using that dependency injection stuff we were just talking about with the solid principles. And then it turns around and it does essentially a vfork of the whole process. So you'll do a copy on write access to all the memory that's located in the Zygote, and all that code, all the Java libraries and other things that are otherwise rather slow to load are pre-conditioned, pre-initialized when the system starts up, and you get the advantage of copy on write optimizations, which is built nicely into the Linux kernel and the hardware support. So as a consequence of this, it doesn't take very long to start applications, even though they have a lot of Java involved. So it's a really clever way of being able to deal with the fact you're on a resource-constrained machine. Doesn't have the world's fastest processor, although they're getting pretty fast. Doesn't have the world's largest amounts of memory, although there's a lot of memory nowadays. But it's still a way of being able to make the device usable at the price point and the resources that they can have. Another big thing in Android, touch-based interfaces. I believe it is possible to buy Android devices with physical keyboards, but you really have to look long and hard to find them. They are not at all very widely used. Which is kind of interesting. I mean, it just gives you a sense of the way in which Steve Jobs changed the world by convincing everybody that the touch screen was the way to go. Do people remember, anybody here remember early attempts at trying to use tablet-based computing prior to the iPhone and the iPad? Does anybody remember that? I was at OOPSLA, which used to be the flagship conference for object-oriented applications and system developers and so on. It's now been renamed to Splash. I was there, gosh, many, many years ago. It was probably a dozen or more years ago. And Bill Gates actually gave a talk there. And one of the things he did was he introduced the tablet that they had come up with. And the big thing that they were very proud of at the time was, unlike those earlier attempts at touch screens like the Newton, which had a hard time reading people's handwriting, the Windows tablet at the time was pretty good at reading your handwriting. And you had a stylus and all this kind of stuff, and it was all sort of written out. Well, what's so funny is almost nobody these days would even think of that as a sensible way to do user interface. Trying to sit there, first of all, I don't know about you, but I've pretty much forgotten how to learn. I've forgotten how to write, since I never write. I type everything, even if it's with my thumbs, I still type. So they attempting to try to find a way to let a computer figure out your handwriting, which gets more and more sloppy over years of disuse, was just the wrong paradigm in many ways. So the touchscreen was a much more effective way of doing things. So touchscreen obviously is built deeply into Android. If you ever have a chance to play around with the source code, there's a lot of cool stuff in there related to gesture detectors and motion events, and it's kind of cool if you really look at the whole food chain from the device driver that's deep in the hardware and the firmware that is detecting your key presses or your finger presses on the screen, and those get turned into events and they're passed up from the driver up to the Java level. And then there's a library called the gesture library that tries to figure out what it is you're actually doing, whether you're doing a swipe or a flick or a scroll or multi-touch kinds of things. Really, really interesting example of composing together low-level events to make higher-level understandings. So that's obviously another big part of Android, the touch-based interface. Largely open source, vendor agnostic community. I say largely because the core parts of Android are open source, but some parts aren't open source. There's some apps that you're more or less likely to run into. We'll actually talk about a few of them later, like the Maps application or Gmail or YouTube, that are not open source. But the bulk of the operating system, the bulk of the middleware, the virtual machine is all open source. There are people who know how to compile this stuff, probably people sitting in this room, who know how to compile Android from source and modify and make changes to it. So that actually had a big impact on a lot of things too. And the way in which the source code is released and the way in which it's vetted and people take it and customize it and do interesting things, that's another part of the scope of Android. It also affected the architectural design. We talked last time about the user space level hardware abstraction layer, the HAL, and that was put in there intentionally to allow vendors to hide certain implementation details in a way that would not be available in open source model, so that they could maintain their proprietary advantage. And another big thing that Android did was focus on the installed base of Java programmers. There are a lot of people out there who know how to program Java. Java is a fairly straightforward language to learn. Most people these days are learning it in CS 101 courses like we teach here at Vanderbilt. And so as a result, you're in pretty good shape to do that. So that's kind of the context. And you can see more discussions of this at the Android website. So what then is part of the commonality? If that's the scope, what's part of the commonality? Well, the easiest way to look at that, to figure that out, is look at the layer cake diagram that Android has. So you just kind of jumps off the page and hits you there. There are lots and lots of common pieces throughout the Android ecosystem and infrastructure and architecture. Some of the ones we're going to be spending most of our time focusing on in this class will be things like services or content providers or broadcast receivers. We'll be starting with activities because you need to have that in order to be able to make sense out of user interfaces. But those are all examples of common components. They're part of the core architecture in Android. Yeah?
For content providers, is there any at all sort of data protection for apps? Or like, the way I understand content providers is that any app can get the content that it's providing. Is that not correct?
You have to have the right permissions.
Okay.
And we'll talk about the whole permission system later. Sometimes when you read about content providers, they emphasize this idea of they're there for sharing of stuff, and there is some of that going on. But oftentimes it's shared in a very, very narrowly defined way. So, for example, if you take a look at many of the default apps that come with Android, so you look at Contacts, you look at Calendar, you look at MMS, SMS, you look at the browser. You'll find that all of those things have content providers that are used for various keeping track of various things like SMS messages or email or calendar events and history. If you do various kinds of history searches, typically those content providers are matched pretty much one-to-one with a given application, and only that application or other similar applications that are given explicit permission, granted explicit permission, can get access to that. So it's pretty well secured. There's some other things that are common as well. We'll talk about a lot of this stuff as we start talking about activities. We'll talk about activity managers. That's one of the things that's there. Package managers, which are used to be able to download apps and install them on the phone. Things dealing with location management. There's a lot of common services and common service implementations that come by default on the system. And then the vendors can decide how much they want to go along and customize that. We'll talk about that more in a second. So there's a lot of stuff that you get out of the box that knows how to handle certain kinds of things. And then there's also a common infrastructure. So there's things like the Intents framework. One of the more interesting and powerful features of Android is this idea that you very rarely tightly couple one application or one part of an application with another. Instead, you develop your applications as a set of building block components, activities, services, and so on. And you make it so that those components describe how they can be accessed and what properties that they need to be provided. And then there's something called an intent, which is basically a data structure that keeps track of various things. And the Android framework, the Android infrastructure, matches various intent declarations saying, I want to be able to view this address, or I want to be able to read this file, or I want to be able to send this email, etc. And then it goes out and it searches for the various components in the system that know how to handle that kind of thing. And once it finds them, then if there's an unambiguous match, it just goes ahead and launches it automatically and starts it. If there's ambiguity, you typically get a little dialog box with a chooser that you can select which of the things you want to use. And we'll see some examples of that here very shortly. So some examples that the Intents framework is one thing. There's a really powerful support for inter-process communication between various parts of Android, either from apps or activities to services or to system services, either user-based services or system-based services, using something called the binder. And we're going to spend a lot of time on the binder in this class. It's one of the real interesting features that you don't normally get exposed to very much if you're just looking at simple ways of doing Android, simple ways of doing user interface development. The binder implements a pattern called the broker pattern, and we'll spend a lot of time talking about that. There's also a neat framework for being able to do web-based application development called WebKit, which is actually provided by Apple, of all strange things. Apple provides an open source framework called WebKit, and the Android browser infrastructure uses large parts of WebKit for various rendering and management of frames and other kinds of web browser-like activities. There's a hardware abstraction layer. There's the OS device driver framework. The device driver framework, of course, is one of the classic examples of frameworks and product lines where you can have a common way to plug in all kinds of different devices that do a myriad of different things through USB or other connections as well. So that's the common part. And when you first learn Android, you're well advised to start by looking at the common parts to figure out what the architectural pieces are. And then as you get more into it, you'll start figuring out what those do. And the best way to do it is to kind of do it recursively. You understand the kind of the big picture view, and then you start diving down a little bit to learn each one of them as you need to know that part. There also, of course, are a bunch of variabilities. Now keep in mind that my discussion here is at a fairly macro level. As you start diving down into each of the layers or components in Android and apply scope, commonality, and variability analysis, you'll end up with similar kinds of analyses. You'll end up seeing this recursive approach. So some of the variabilities include things like product-dependent components. If you buy certain versions of Android smartphones, like the one from HTC or the ones from Samsung, they will have their own proprietary look and feel. They'll have their own proprietary implementations of various things. They might have their own proprietary hardware drivers for their particular way of doing touchscreen interactions or physical keyboard interactions. There may be other kinds of sensors that are built in. Some phones have, very accurate accelerometers. Others may not. If you're buying a phone or developing a phone that's intended to be used by, gaming community, you may have different kinds of things in there because people might be using your phone as a game console. If you're not doing that kind of stuff, then you won't have the extra cost for the hardware. And then there's also different product-dependent assemblies of the components. So this sometimes depends on hardware, sometimes it doesn't. Depending on who you get the phone from, you may get certain apps bundled. Almost everybody comes with sort of the core sets of apps that are part of Android. Some of the ones listed up here, things like a calculator or a media player or the calendar or email. But some vendors will give you their special purpose versions of these things. Some people may implement special purpose MMS applications or SMS applications. Some people may implement different versions of email. Most phones come bundled with Gmail, but that's not an open source implementation. Depending on whether your phone is intended to run in the US versus Europe, you may have CDMA versus GSM hardware and software that goes along with it. Some phones run in both. I just got a Galaxy S4 just the other day, and that has a dual use capability. You can take it here, you can take it to Europe, and it should work both places. And there's all kinds of other configurations, different versions of the operating system, different versions of the hardware. So there's lots of places where things may be different as well. And as I mentioned before, we can apply this whole approach recursively throughout the different layers. And I'll do that as we go through activities, as we go through services. I'll keep pointing out, here's the part that's common, here's the part that varies. And that hopefully will help you see the pieces and how they fit together. So, to wrap it up, scope, commonality, and variability analysis is a general purpose method for trying to develop systematically reusable artifacts and assets. And the other important thing here is that the real goal here is sometimes hard to see if you only build applications. If you're only an app developer, you might be a great consumer of scope, commonality, and variability analysis, but you may not see the need to learn those techniques yourself. Conversely, if you're an infrastructure developer, if you go work for Apple, if you go work for Google, if you go work for Sun or Oracle or IBM, those types of companies tend to build a lot of this kind of software. And so knowing how to keep track of all the variabilities and do them in a consistent way is very, very important to try to keep from being crushed under the weight of software complexity. And so the end result is Android provides a very nice example of a product line architecture with a whole pile of frameworks that simplify the development of mobile applications, both tablets and smartphones and other kinds of devices, in a resource-constrained domain. Okay, any questions about that? So let's switch over now, and we will start talking about activities. So up to this point, we've really only been talking in general terms about the concepts of Android from a high-level architecture point of view, some of the framework dimensions with a few examples here and there of some of the Android capabilities. Now what we're going to do is start diving in systematically through all the different parts of Android and looking at it in more detail. Now, as I mentioned before, this class is primarily a class on systems programming. So we're going to do a lot of stuff with inter-process communication, things that run in the background, different multi-threading models, different ways of being able to do network communication, different ways of being able to access persistent data in various ways, doing queries and other kinds of access. But you don't get very far if you don't know some way to be able to get input from users and give them output. It just isn't very interesting unless you're building, headless embedded systems in Android, which is conceivably doable, but a rather unusual thing to do. So we're going to start by talking first about activities. And your first assignment, which we'll go over here by the time the class is almost done, will give you a chance to start playing around with this thing. So what we're going to do here is we're going to talk about how we use activities to provide a visual interface for users to interact with the applications and the services and capabilities that we're providing. And again, we'll cover commonality and variability analysis throughout the discussion, so you can see how the activity portions of Android are also based on this commonality and variability model. So what's an activity? An activity basically provides a visual interface for user interaction. And an activity typically supports one thing a user can do. So it might be give you some way to log into a service, or you might be able to compose an email, or you might be able to view a contact, or browse the internet, or locate someone who's a friend through some kind of mapping service or whatnot. Typically there's one thing with a handful of variations that an activity can do. And what's interesting about this is not so much that each activity does one thing, it's the coolness that Android provides you to be able to take all of those one things and put them together to form more complete applications and application experiences. An application can include more than one activity. And you'll see that applications can actually use activities that are defined by other applications, which is a pretty cool thing that you'll get out of Android. Certainly not unique to Android. Other people have come up with this notion of component models and component loosely coupled, loosely bound components before Android came along. But Android, I think, is one of the first widely used mainstream approaches to take this to the extreme that it does. So just as an example of this, if you take a look at Eclipse, here's an Eclipse project. We'll look at this a little bit later. And you come in here and you look at the manifest file and you click on the application tab and you go all the way to the bottom. You can see that this particular application that I have has one activity. And as I define more, I could go ahead and associate them together with the parts of Eclipse to keep track of those activities. Okay, so the main thing to learn about activities, and we'll cover this in a second, is the notion of a life cycle. And there's some good resources you can find on the website to talk about that. In addition to activities, there's also something in Android called a task, which is a little bit confusing at first, although once you play around with an Android phone for any length of time, it becomes pretty obvious what tasks are and how they work. A task is basically a chain of activities, and the tasks don't have to be provided by a single app. You can actually have multiple apps that are running, and they will be providing different activities in the context of the task or the task chain. And there's a nice website you can go to that talks all about tasks and how to manage tasks. We'll talk about that in a second. Tasks are really cool because they give this illusion that you have a single app, but it's actually composed of a number of unrelated activities. So why is this important? Because it helps us to be able to get systematic reuse. We can build our user-facing components in terms of building block activities, and we can put those things throughout our system by use of declarative mechanisms through an XML interface called the Android manifest file. And then in conjunction with some other magic that comes along with Android, like package manager and activity manager and so on, as you start running your application, it can leverage existing components like activities in order to be able to give users a seamless experience where the actual application developer really didn't have to build the whole thing. They only had to build part of it, and then they can script and compose the other parts in very flexible ways. So it's kind of like what you'll see if you're familiar at all with the concept of Unix pipelines on the command line, and DOS can do this a little bit, but Unix is much more sophisticated at it. With a Unix environment, you can have a string of utilities that get combined together in a pipeline where the input for one activity is going to be coming from the output of another activity or another utility or process or whatnot. And that's a linear way of data to flow through a system. What Android gives you is something similar to that, except instead of having a pipeline of these things, you can actually have a graph of them. And so it's much more flexible and much more composable and much more dynamic and cool in lots of different ways. The activities that are part of a task are stored in something called a backstack, with the currently running activity on the top of the stack. And if you have an Android phone, like this is just a screenshot I took of my phone earlier today, I had a bunch of activities that were running, and you go and, depending what kind of phone you have, you press a button and it gives you a view of the stack of activities, and you can move around in that stack and switch back and forth between the different activities. There's also another way to do it, and we'll see this in a second, much more simple. You just use the back button to go back, and that's another way to go. So at runtime, whenever an activity is launched or started, and we'll see in a minute how to do that, it's by default placed at the top of the stack. There are other ways to manipulate the activities programmatically, but the default way is when you spawn them, they go to the top of the stack. And then they start to run. And we'll talk about how you get to program all that stuff and how you interact with various things. And when you're done with your activity, then you go ahead and hit the back button, and that causes the currently running activity typically to be popped off the stack and destroyed, and then processing resumes at wherever you were when that activity had been started. Whatever had launched that activity is typically where you end up with, going back to. And there's various ways to control this as well. So you can kind of see here we have an application that is running Gmail. And we go ahead and we hit compose. And then we go ahead and we write our message. And then when we're done, we go back, and it takes us back to some conversation list, and we go back again, and we're back to home. So all those things are defined as different activities with different screens, and yet the way in which the Gmail application works makes them all appear as if they're part of one seamless application. Here's a little view that shows what this looks like underneath the hood. So let's say we start out with our phone in home screen mode, and we go ahead and start an activity. We run a program like the programs that you guys will eventually write here that displays various various bitmap images. And what happens there is that activity gets pushed onto the top of the backstack. And then if you start another activity, if this application launches another activity like a map application or something, then another activity is pushed on the stack, and you can kind of see it pushes the ones down below. And at some point when you hit the back key, that turns around and navigates back. The activity's popped off the stack and destroyed. And we'll talk more about how you can control what happens as those things occur. Because oftentimes when an application activity is destroyed, you want certain state to be maintained or preserved someplace. So if you come back to it later, you can pick up where you left off. OK, any questions about the concept of a task or activity? These are good quiz questions. What's a task in Android, and how are activities managed, and so on. So let's start talking about implementing activities. That'll be the first thing you'll be doing in the assignment that's due a week from today, which is intended to be very simple, by the way. So the first thing that you do is you typically inherit from the activity class, either directly or indirectly. Your first assignment will actually have you inheriting indirectly from activity for reasons that will become more clear in a minute. For debugging purposes. And so you might say, I have a class called myLocation, and it extends activity. And then you come along and you override, using inheritance and dynamic binding features in Java, which are just like the ones in C++ in this respect, you override selected lifecycle hook methods. We'll talk a lot more in just a minute about what a lifecycle hook method is. The most important lifecycle hook method is the onCreate method. That's the one that's going to be used to initialize the activity when it first starts. And then we'll see how, depending on what happens, other hook methods may be invoked automatically. And then you'll include this activity in your Android manifest.xml file. And this is the file that's used to describe which particular pieces of things are going to be exported to the outside world, which ones are going to be used, various permission issues, and so on and so forth. They're all described declaratively in the manifest file. And there's various ways to access this. You can either look at it as XML code and you can manipulate the XML code directly, which is what I like to do, or if you don't feel quite so comfortable with crazy angle brackets, there's other higher level ways to do this as well. Someone once said that XML syntax is like Lisp with horns. And they're probably not too mistaken on that. Lots of crazy angle brackets here. As things occur in the Android runtime, it's going to call back to your activity as different lifecycle states happen or different events happen that you need to be informed about in order for your activity to do something sensible. And we're going to take a look at what these things do in a second. But first, let me just talk about commonality and variability, because that was a big part of this. So from a commonality point of view, the activity class and the methods that you inherit provide a stable interface for all the different kinds of events that your user interface view needs to be aware of. So creation, destruction, starting and stopping, pausing, resuming. Each of those things has a specific meaning in Android that gets invoked at specific points in time, and there's lots of good documentation to learn about what those things do. And your first assignment gives you a little help with some debugging tricks to keep track of this for your own knowledge, so you can learn how it works. So that's the commonality part. Every activity has those same hooks. By the way, the other components in Android that are important, like services, content providers, broadcast receivers, they also have a bunch of hook methods too. Services have slightly different hook methods that activities do, but they get called back in very well-defined places. There's also some other stuff that are often used along with activities called fragments, and they have even more hook methods. We'll talk about those later. We're not going to talk a lot about fragments in this class because it's not really a user interface class, but modern best practices in Android use fragments very heavily. The variability part is what you do when you customize the activity. So that's where you do something specific for this particular type of service or application behavior when you subclass from activity. You fill in on create, you fill in on destroy to do the right kind of thing for your use case. There are a bunch of different states that the activity can be in based on its life cycle. So there's a bunch of things that happen at startup time. So when you start an activity, by calling start activity, there's a bunch of hook methods that get called back automatically. On create, on start, and on resume are all called when you start an activity. And we'll talk later about why there are three of these things, not just one of them. While the activity is running, then various things can happen. You can pause an activity, you can resume an activity, you can stop an activity, you can start an activity that was stopped, and so on. And so basically it provides a state machine that you can transition through. And you as an application developer are responsible for keeping track of what state, Android is responsible for keeping track of what state the system is in, and you are responsible for doing something to your application state or data based on the state of the activity. And this is important to be able to make sure that you don't misuse resources. Remember before we talked about scope? Resource constrained system, we can't afford to keep everything running all the time. So one reason why Android does all this stuff is to be able to make sure that you have as little in memory as possible based on how your activity or your application is being accessed at any given point in time. So when an activity is no longer at the front and center of the user's user experience on the phone, the resources it has can be removed from memory largely and or put back into persistent storage for later use. And then there's also a way to shut things down. You can voluntarily have your system, when you are shut down, say when the back button is pressed, and you voluntarily finish, you can destroy things. There's also situations where the system will unilaterally come along and decide your time is up, and like an existential movie by Ingmar Bergman, you play chess with death or something like that, and it decides your time is up. You've lost the game of chess with death, and it shuts you down. This is one of those things, once again, that was put in there because it was a resource-constrained system. And if you're really running low on memory, Android gets pretty draconian pretty fast to kill off all the things that don't need to be there. Now, the good news is, as phones get lots and lots of memory, this becomes less of an issue. But back in the early days of Android, activities were being shut down quite a bit because there simply wasn't enough memory to run everything. So take a look at this URL for more information about these lifecycle events and the lifecycle states. The way this is handled under the hood, I encourage you to take a look at some of the online resources available at the Google I/O site that'll talk more about how activity management works in Android, and they'll talk about the infrastructure of how this all works. Here's a picture that illustrates this. As you can see, if you look at this picture, there's something called the Service Manager, which is responsible for managing a bunch of services that are started when the phone begins to run, when it first boots up. And one of those services is called the Activity Manager. And it's the thing that keeps track of the activity lifecycle and then arranges to get those callbacks to your hook methods that you define. Now, we won't do this here, but if you were actually to look in the code, you would discover that they use the template method pattern very heavily throughout the implementation of all this stuff. And so in a sense, your activity that you implement is a template method, well, actually the underlying behavior of Android is a template method, and you define hook methods. So things like onCreate, onDestroy, onStart, onStop, etc. Those are hook methods that get called back by the Android template method, which is controlling the overall event processing of the system. And there's a lot of moving pieces here, so I will not begin to try to explain it all to you, but you can take a look at the source code if you're curious, and it's really interesting. So take a look at the activity.java file to see how these callback hooks are invoked, and then take a look at the activity manager service to see how it gets that over to the activity portion in order to do its thing. Here's a little bit more about some of these hook methods. So the onCreate method is called when an activity is first created, and it's meant to initialize stuff. It's by far the most important and widely used of these callback methods. OnStart is called when the activity is becoming visible to a user. So typically creation only takes place once, but then under various circumstances you may lose or regain focus of a user's interest in activity as they manipulate that backstack, or they manipulate other ways of managing the different activities in the task through the task manager. OnResume is another hook method very similar to OnStart, which is called when a user returns to an activity from another. Let's say you want to compose an email message, and so you hit compose, and it gives you a chooser to choose from a list of people to send to. While that has come up and it's blocking the compose activity, and you're selecting from your contacts list, that's actually stopped the underlying compose activity while you're going ahead and selecting the list of people from the people finder. So when that activity that's blocking is done, then we're going to restart the one that's underneath. So stopping and starting is a little different. That's when you're about to become visible or not. And so there's onStop. When a user leaves one activity for another, the current activity that's being pinned is stopped, and that gives it a chance to free up any resources so we don't hog system resources. And then onDestroy is called when an activity is released and needs to clean up what it's doing. So one of the things I'm going to have you do for your first assignment is implement a very simple helper class called the Lifecycle Logging Activity class. And its only purpose in life is to make it real easy to learn when these things are getting called. So what you'll do, instead of inheriting your activity from activity, you'll make a little helper class called Lifecycle Logging Activity, and it's going to go ahead and define a bunch of hook methods that are going to be called to print out to the logging interface, or the logging system, what's happening, so you can quickly see at a glance what's going on in your system. So when we talk about the assignment in a second, you'll see how that works. So we inherit from the activity class and then automatically have these hooks to provide some useful debugging information. Note, by the way, the use of inversion of control. I've mentioned many times that Android is full of frameworks. This is a great example of this. You do not own the event loop. Android owns the event loop, and it will call back your activities, your services, etc., when interesting things happen that you have registered for by virtue of the fact that you inherited from activity. And so these hook methods are going to be called back automatically whether you like it or not. And so this is just a way to be able to make sure that you log what's going on. Okay, so what I'm going to show next, and actually in the interest of time, I'm not going to show this today. I'm going to talk about the assignment next, but I'll load this stuff up and you can take a look at it. This is a very, very simple map activity that's similar to the one you're going to be doing for your first homework assignment. And basically what you do is you enter in a location, and it then goes ahead and pulls up a map and shows you a view of that location. And when we come back next time, we'll go through this in more detail. We'll talk about how the different things are called at various points along the way to start this stuff up. And we'll talk about how this works and how you start applications and so on, start activities and so on. But what I want to do now, in our remaining time, is switch over to the class website and go through the assignment. So the purpose of this assignment, it's very simple. The people here who programmed Android, it should probably take them about 10 minutes to do it. People who have not programmed Android, it may take you longer. As I say at the very bottom, if you find yourself spending 3 or 4 days on this, this may not be the right class. It really shouldn't be that hard, especially once we talk about the example app to help drive this. So basically the way this is going to work, you're going to write an activity which, when launched, will prompt the user to enter in latitude and longitude coordinates. And you can figure out, you can use other programs to figure out interesting latitude and longitude of things that you care about, like Area 51 or something like that. And once you enter that stuff in, then it should go ahead and display the results on a map. Get that a little bigger so you can read it. And of course, you can do this either through the emulator, or you can use a real phone. For reasons that we'll talk about in just a second, if you have a real phone, I strongly encourage you to use the Android phone because you'll find it's a heck of a lot easier to work with and it's way faster. If you don't have a real phone, don't despair. You can still use it there. It'll just be a little bit more somewhat convoluted for various reasons we'll talk about. So here's how you are supposed to implement this. Have some class called something inspirationally interesting like map demo activity. And in fact, why don't we make life easier for the TAs, and we'll just call it map demo activity. That'll make their lives easier. And it's going to use a text view object to prompt for the location. That's these things, the location part. And then it'll store that into a couple of other edit text objects. And then we're going to have a button object. You'll have to write a button object that will, or you won't write one, you'll use one, as we'll discuss in a second, that'll be labeled show location. And you're welcome to make this look as simple or as sophisticated as you want. Turns out it's fairly simple to do this. Bare bones is just have a button you can push somehow with your finger that shows the location. And this whole thing has to be done in a way that does not have you writing that button click code directly in your activity. So what you need to be able to do is you need to be able to understand how to define this using the various resource files that Android gives you, the layout files and so on that you have, or that Eclipse will make for you on your behalf. And then you have to figure out how to connect together the layout described in the XML file with the appropriate callback method that's part of the activity that you're dealing with. Not a hard thing to do, just have to figure out how to do that. Also, make sure that you do a little sanity checking on the input from the user. If they give some crazy latitude and longitude value, then you need to pop up a toast and say, hey, you're giving me the wrong values, and go back to a sensible state. Your program shouldn't just crash randomly because people give you bad input. That's not good form. And then here's the part that's fun. So once you finally got the input, the latitude and longitude, that's correct. What you then need to do is you need to be able to start an activity to display this thing on a map. And there's a couple of different ways to do this. So one way to do this is to create an intent that uses the geo prefix. And we'll talk a bit more about that on Wednesday. You can read ahead a little bit. It's not too hard. It's a URI that has the geo prefix on it. And you just give the geo prefix and the latitude and longitude and a few other weird syntactical conventions, and then you create an intent that has all this stuff bundled up as part of its so-called URI, which is its data field. And then you go ahead and you say, I want you to view this, Android, I want to view this intent. I want to view this URI. And you do that by calling start activity and passing the intent in. And through the magic of the intents framework, then that should automatically start to run, and something good should happen. It should show the map. Now, for reasons that are somewhat mysterious, if you are using your Android phone, this will work perfectly fine. If you're using the emulator, this will not work because, for various reasons, maps don't come, the maps capability doesn't come as part of the emulator. You have to have a working phone. But don't despair. It's easy as pie to be able to use a browser to do the same thing. So you simply have a browser and you'll open up the Maps application and you'll pass this thing in as data to the URL that you have for that. And so if for some reason you can't get it to work with the Geo URI, you can use a Maps browser URI instead. And now what your application needs to do is figure out which of those things to use, and you should be able to write code. This is another part of the assignment. You should be able to write code that works correctly whether it's running in an emulator or on an actual smartphone. And there's various ways to do this. One way to do this is to try to start the activity. If it fails, you catch the exception, and you go ahead and fall back to the alternative model and try that. That's one approach. The other approach, which you can read about, whoops, here, if I ever get my links set up here correctly. I'll have to fix that. If you go here, it tells you the tricks to be able to verify that there's an app to receive an intent. And it basically uses some magic in the package manager, which is a cool reusable service, systematically reused, in order to be able to query to see if that particular handler for that particular kind of intent is available and registered in your system. So this illustrates a little code that will help to make that easier. And let's see, a couple other things. Again, don't hard code the layout. Use the XML layout files to do that for you. We'll talk a little bit more about that next time. It's really straightforward, but you have to learn how to do that. And you should also see the output of your program written in some sensible way to the logcat log file. So you should see things like on create started, on create called, on start, on resume, or whatever you end up using there, it'll tell you, and that's a good way to learn what happens. And I recommend that you take your very simple app and try a couple of different things with it. Notice how, for example, when you launch the browser or the Maps app, if you look at the log, you'll see that your app, your one that you're writing, gets paused and stopped, and then you'll see the other one starting up, and you may or may not get any diagnostics for that one because you didn't annotate that code. But when that other app, when you do the back button on the Maps application, then you'll see that you're resumed and restarted. So it's interesting to watch those events go back and forth, and that's a good way to learn the circumstances under which the lifecycle events are triggered by callbacks from the framework using the template method pattern and the other stuff we were talking about within version of control. Okay, so you can find a lot of information about how to do this if you take a look at the Busy Coder's Guide to Android Development, which is the text that I recommend you use. You can invariably find other descriptions elsewhere around the web because it's not a very hard assignment. I'm just giving people a chance to get up to speed. After this assignment, we're going to get a lot more interesting. This is just a one to get started with, get people up and running something, and I'll also get a chance to review all your code and see who needs help with using Java, using patterns, using different kinds of stuff. Okay, any questions at this point?